and welcome to the Age of AI podcast. On the show, we talk to entrepreneurs and innovators all over the planet who are using machine learning to transform their industry. And we mean real-world applications with tangible business value, not just research projects. This podcast is produced by Sanfram Transnational, which is a global education company helping non-technical entrepreneurs and executives become technically fluent. Thank you and hope you enjoy the episode.
Hello everyone, welcome again. I'm your host Aman, and today I'm speaking with a new, very special guest, and I'm going to try to pronounce his name now. Otto Söderlund. Was that okay? Otto?
That was perfect.
Okay.
Perfect.
And Otto is the CEO and co-founder of an AI company called Speechly. And Speechly is working on a really interesting product that helps people control devices via voice commands, right? And although the concept itself has been around for a while, you have voice assistants and whatnot. I wanted to discuss this company because the way their product works, I wouldn't be surprised if this approach is really the one that helps a lot more companies start adopting speech commands for their products. And we're going to get into why that is and how their approach works. Otto, thank you so much for joining us. Super excited to have you.
Absolutely. Thanks, Aman, for having me.
Cool. So to set up the big picture, because it's a very technically complex product that you have there, let's start with an example of something that people are already familiar with, right? The big search engine company has their product that everybody knows about, and the big e-commerce company with the name starts with A, they have a product that everybody knows about. At a high level, how do they work? Like, what are the inputs and outputs, and what's the evolution been like for before Speechly came into existence?
Yeah, sure. Maybe I can tell a little bit about the kind of history of this field overall.
Yeah.
So
Yeah.
speech recognition is it's not a novel field. So I think that the original research in speech recognition started already in the 50s or something, and
Yeah.
it's something that there has been a lot of interest in, and it's been part of the original waves of artificial intelligence interest back in the 50s, 60s. Speech and audio was an instinctive and natural way or an interest area for early artificial intelligence researchers to look into. And basically, it has been studied for over 50 years, 60, 70 years. But throughout that time, there were quite limited applications because the accuracy was still in its early stages. And I think it was in the 90s when the first proper applications for speech recognition started to appear. And there's companies like, for example, Dragon, who started building these applications, who built on top of the back then state-of-the-art speech recognition, where the accuracy was already something that was valuable enough to assist in certain domain-specific use cases. But still, back then in the 90s, in the 00s, in the 010s, it was still pretty far away from human ability that speech recognition technologies had. And it was basically only until, I would say, around 2016, 2017, when the technology started to reach a maturity stage where it started to be really, really useful in supporting practical use cases. And I think it was in 2016 when there was the first academic paper, seminal paper, produced by one of the big internet companies, where they showed how a speech recognition technology that was state-of-the-art back then was able to achieve human parity. So basically be as good as a human person in understanding speech.
Was that deep speech?
That was before deep speech. So
Okay,
that was earlier. So that was this paper was on Microsoft Research. And it was really the first academic peer-reviewed paper where human parity was in a way demonstrated in practice. And this is also the same time when there were already started the first assistant technology started to emerge. So Siri was really the innovator in this space, and when Apple introduced that 10 years ago, then it was quite a big thing, because it was the first kind of mainstream adopted voice technology product for the consumer market. And I think that
Yeah.
that made quite a lot of waves and set the expectation levels. But still back then, 10 years ago, the technology wasn't really mature enough to work outside very specific limited range of use cases. And since then, the majority of the interest and focus in the whole field has been revolving around assistants. And we've seen many of these big tech companies. Maybe I will mention the names: Apple, Google, Amazon, who have all invested heavily in their assistant technologies. Also Microsoft, Samsung. So we can see that the big tech is really interested in these technologies. However, a lot of the motivation for these big tech companies on investing on these voice assistants has been really driven by the extremely tough competition of the consumers' time spent with different medias. So all of these companies are really trying to claim more time of the time that users spent with different medias and of their day. And they are really trying to create new platforms. They're kind of trying to do a new app store, but for voice applications. So that has really been driven the innovation in the last years, and it's only until very recently that we've seen novel approaches in the industry.
So let's get a little more, granular with this, right? So let's talk about, for the big picture, what are the different types of speech recognition models or approaches that there are. So for example, and at the highest level there are different applications, right? Speech to text, speech to different speech in a different language. So what can you delineate, like how, like when you say speech model, when people generally say speech model, what are the different types of speech model in terms of the big picture input and output? What exists right
Mm,
now?
So focusing really first on the task of understanding the human. In
Yeah.
there, how it typically goes, that there are different steps in the processing, where the first step is really translating speech into text. And that
Okay.
basically means changing or translating audio signals into characters,
Yeah.
basically.
Yeah.
And that's the first step of the process, and it's very straightforward uh, signal processing task of really interpreting audio signals into letters and words.
Yeah.
And the next step in a traditional or let's say traditional pipeline, you could say, is then, okay, now that we know what the user has said in words, now what is the user meaning? So what's the meaning that we want to extract? And this is the natural language understanding or natural language processing, depends on how we define those terms, part. And that really
Yep.
takes text as an input, and then figures out what the user is meaning with that utterance, is the
Okay.
name of these textual units that are processed in this field.
Yep.
And typically that part of the process then returns indents, entities, maybe some additional information, like more information about the speaker or about the tone of voice and so on. But typically most applications really are built on top of indents and entities. And
And
when these are
just
then,
for one
yeah.
second, just to explain to any people who are non-technical who are listening to this, when you say intent and entity, let's say you have a sentence like Jimmy wants a banana, right? So
Mm,
in this sentence, Jimmy is an entity, it's a name, it's a proper noun. Banana
mm-hmm,
is also an entity, it's an object, right?
mm-hmm,
And wants is kind of shows the intent. So want
mm,
is like, can be classified as wants or desires or whatever. That is one type of intent. And so that is how you split up a sentence into entities and intents, and that acts as one more layer of data that sits on top of the text, right? So you get, okay, I speak the sentence, Jimmy wants a banana. That gets converted into the actual text, and then from
mm-hmm.
that text you extract these entities and you label them, right? And so that's where we've gone so far. Go on, Otto.
Exactly. Well summarized. Well summarized. Great. So then we are in a situation where we know what the user has been, what has been their intent, and what are the entities they've named. And that's when the kind of application or domain specific task logic starts. So you need to figure out, okay, so if in my application the user wants to do this and they have mentioned X, Y, and Z as the entities, so how should my application respond? And how should the user experience then respond?
Yeah.
And then when this logic is then done, then the next step typically is then in traditional systems is to actually provide a synthetic speech voice back to the user. So a text to speech step where
I see.
the outcome of the logic, what to answer to the user is then translated back into speech to the user. And this is how basically the majority, like 95% or 99% of all of the current voice technology systems basically operate according to these steps.
Okay, so you go from speech to text and then to the entity and intent layer, and then you do some your own different whatever synthetic domain specific response you want to provide to that based on that entity layer. So you draft a response and you put it into text, and then you have another model to do text to speech, right? And you give a
Yes,
response
exactly.
to the consumer. Okay, and this is how, and it's very sensible. Of course, like if you were to sit down and draw up a plan for how you would do speech voice assistant, that yeah, it makes sense to do it this way, right? What
Yes.
is the okay? So in this thing, like what is the state of the art in terms of, let's say, lag or delay time or speed of this whole process happening, and accuracy, and where are the shortcomings, where does the accuracy lag, where are the missing gaps that haven't been solved previously?
Hmm. That's great. So starting with the accuracy question and proceeding with this kind of sequential process.
Yeah.
So starting with the speech to text. So in speech to text, I think that the uh, human parity has already been reached in accuracy.
Okay.
So typically there is this magical number of 95% because
Hmm.
humans also make errors. So
Yeah.
typically there is this golden number of 95% is the accuracy for humans. And that has been shown to be surpassed many times. But of
Hmm.
course, when there are challenging environments, challenging acoustic environments. You're on the move, you're on the car, you're inside a factory, you're inside a noisy environment. Then humans start to struggle, and so do machines. Still
Hmm.
today, machines struggle a bit more than humans. So humans are a bit better in recovering from the problems arising from the noisy
Yeah.
environments.
Yeah.
And many of the practical applications, the use cases where you can actually get a lot of value out of this speech recognition powered systems actually happens in environments that are not clinical studio environments with perfect sound environments. So that means that kind of like the 95% number is in a way a theoretic number. In practice, it depends a lot on the acoustic environment, and it's all about whether it's better than the human working in a similar environment.
I see. So a
So from the speed,
95% is 1 in 20 words, right? 1 in 20
yes,
words is, it's still okay. I mean, like you could say depending on what kind of word is missed. So if it's an entity or an intent that you mistake,
yes,
I mean, if I mess up a proposition a little bit, that still makes sense. You can gather from the context. But if I mess up a proper noun, like the name of a person, and I talk about somebody else, that's a different. So in that context, where is the error rate really happening?
so you are right that of course the most important part is where does these errors happen, and whether how meaningful are the parts
Yeah.
where they are happening. But I think that when considering the accuracy rates, it's important to understand that human communication also has a similar 1 in 20 words errors, and
Yeah.
still we are able to communicate and we are able to process the tasks even though
Hmm.
we do miss words, and
Yeah.
that's
Okay.
that's 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 kind of like normal. So
I
I
see.
think that it's unrealistic to expect a system, especially a machine learning system, as you
Absolutely.
know, people in the field know, will never yield a 100% result. So that is anyway unrealistic, and that's why the better comparison is basically being able to achieve human parity, so work at least at the level of a human working on an equivalent task.
I see what you mean. So when we say human parity is 95%, it's really the same 95% in the same context. Not that you set a number 95% and then you miss very important words, but you still classify. It's the same as humans in a way, right? That's what you're
Yeah,
saying.
exactly. That's
Okay.
yeah, because in some domains, some contexts, it might not be 95%. It might be very
Yep.
difficult for the human to actually be able to even operate in that kind of environments. And it's possible in
Yep.
some environments humans are not able to communicate. Imagine very noisy industrial environments where there are big machines making huge noises and people having hearing protection and shouting to each
Yep.
other. And that it's not a very effective
Yeah.
communication. So everything is in a way relevant or
Okay.
relative.
Cool. So we
So that
covered
was
the
the
first
first
one,
part.
right? Yeah.
Yes, then we go to the natural language understanding, and the natural language understanding field has made tremendous progress in the last couple of years. So there has been a lot of these very uh, famous or even kind of like sexy models that have been released, like GPT-3, and there's plenty of these models, and that has really brought this field light years ahead. And you could argue today already that the NL, natural language understanding field, has basically already reached human parity because it can already understand a lot, and it can already generate amazingly convincing
Yeah.
materials. So that's also an area where if you look at the accuracy there, it is very close to the human parity or even exceeded that. But again, this is always, it's not trivial to measure these ones, but we can clearly see from the applications that have been built, because I think that that's the ultimate proof in the pudding, is that
Yeah.
if actually you are able to create an application that is something that people are willing to use and don't get frustrated and feel that it operates as well as there would be a human person doing that, then the human parity has been reached. I know it's a very subjective definition of it, but I think that that's what is the ultimate goal of building these technologies, is to power applications that normal people are comfortable using. So that's the natural language understanding part. And of course, in speech synthesis, we have already seen these amazing synthetic voices that it's basically impossible for people to distinguish a robot from a human person. So again,
Yeah.
in here, I think that the applications show that the fields have been progressing very fast. Now, when it comes to the latency and the user experience in turn, so if you again divide these parts here, so when it comes to the speech to text part, the speech to text part, typically the latency is that the state-of-the-art systems, how they work is that it usually takes them a couple of hundreds of milliseconds after the user has spoken when they have the final transcriptions ready for the downstream tasks.
Yeah.
So it's already pretty fast, the latency that they are producing there. And in the natural language understanding, we're also talking about hundreds of milliseconds or tens of milliseconds from the natural language understanding to get the text as input in actually being able to extract the intents and entities and potentially other models there also. So if you look at those ones, kind of the part of the sum, the latencies are pretty good. But the big challenge that the current generation of technologies lies in exactly this way how these technologies work together. So they all work in this sequential manner, where the first step that these technologies does is that they translate audio into text. And how it works today is that when the user speaks, when the user has stopped speaking, then a couple of hundreds of milliseconds after that one, the transcript text is ready. And that is then passed on to natural language understanding, that then typically takes tens of or hundreds of milliseconds to process that, and then returns the intents and entities, which are then passed to the business, the domain-specific business logic that
Yeah.
then, depending on the application, figures out how to respond to the user. And that typically takes, depending on how many calls to databases or other
Mhm.
activities they need to do, can take hundreds of milliseconds. And then the last part is then the speech synthesis, which then also has some 100 milliseconds of latency. And even though the kind of the latencies of the individual subtasks feel pretty good, but because of the sequential nature of the processing, the overall the user experience latency of this sequential pipeline leads into a situation where when the user speaks, when they have stopped speaking, they typically need to wait 1 to 2 seconds before they get any meaningful kind of response from the system.
Yeah.
And this is something that everybody who has been using Siri or has been using Alexa or has been using Google Assistant or has been using any of the other assistants out there have for sure experienced. So when you speak to your assistant, what happens is that while speaking, nothing happens. When you stop speaking, then the processing actually starts.
Yeah.
And then a couple of seconds afterwards, you actually get any kind of meaningful response.
Mhm.
And from the user experience perspective, what this means is that there is always this very inherent delay in getting any meaningful kind of response from the system. And this leads into a situation where the paradigm for the interaction is basically always a turn-based dialogue where there is a significant delay between the other party, even though we're talking about virtual party
Yeah.
here,
Yeah.
basically is able to provide a meaningful response to the other party. And this is something that is actually quite unnatural. This is not how human
Mm.
people communicate.
Yeah.
Human people communicate in a way that you, when I'm speaking here, you don't wait for me to finish and then you start thinking about what did Otto say, but you're actually processing what I'm saying
Yeah.
while I'm speaking, and you're actually all the time providing me with feedback while you
Mhm.
are using sounds, but also gestures, nods, and so on. So
Yeah.
human communication is not actually a turn-based dialogue that would only use the voice channel, but
Yeah.
it is actually a real-time, full duplex, two-way communication that uses multiple modalities to efficiently transmit information back and forth. And if you look at the human brain works so that while I'm speaking, it's very hard for me to listen to what you're saying if I'm
Yeah.
speaking.
Yeah.
But if I'm speaking, it's very easy for me to process, visual information in my brain, so I can actually get a lot of information from you, and that's really a key aspect of the efficiency of human face-to-face communication that the current generation of voice technology systems are lacking.
Mhm. I see. So to put it in simple words, yeah. I mean, when I talk to Siri or Alexa or something, it feels like I'm talking into a walkie-talkie, right? Hey, okay, Roger. Okay, like okay, copy. Then the other person speaks when you stop going. And yeah, I mean, when we talk on the phone or we talk to people, it's not like speaking into a walkie-talkie, right? It's like it's a
Hmm.
very different kind of conversation, right? Um, and that user experience factor, which is only like which most people don't even realize that it's actually slow, but they can process it subconsciously that yeah, there's a delay here, it's a turn-based dialogue, it feels unnatural, but it's still pretty impressive, right? um,
Hmm.
and the thesis here, it sounds like, is that if we could fix this little aspect of user experience, of user interface, right, then that would skyrocket the adoption rate from whatever it is right now to seeing it everywhere. Is that the thesis, or is it that, or like, I mean, I'm just thinking of, since we went through this whole sequential process, right?
Hmm.
One more thing that I wanted to point out or and ask your opinion on is the place where you do the natural language assessment, right? You extract entities and sentiments. I feel like, and we took the example of GPT-3, which is I think the biggest deep neural network ever made. It has like a billion or plus like parameters in it. Um, does that really have the latency that we described about, like just a few hundred milliseconds, or and especially one more thing is like these are on mobile smaller devices, right? These are not on a cluster with multiple GPUs that are running and doing inference on these models, because the hardware also makes a difference, right? The same machine learning model on your flip phone, not a flip phone, your smartphone, versus on your laptop, versus on your gaming computer, which you built custom, which you had custom made for high end gaming, is going to have a completely different rate of delay. So my question really is, in summary, the turn-based dialogue is definitely a user experience issue. I totally understand that. Can you throw some light on what other factors are equally significant or almost as significant as that in driving the adoption rate or the ubiquitousness of of this technology?
Good. So there were many questions here. So
Yeah,
I'll start at least with the last last one.
yeah,
So because the individual parts of the technologies have in practice reached human parity,
yeah.
so that means that basically the biggest technological problems have been solved, and that means that the real barrier for people to start mass adoption of this technology is user experience. Because if you talk to people who use or do not use but have tried these technologies, you will see a common thread that people are quite frustrated with how it works, and how it's not kind of that very good. And if you look at the use cases that these technologies are currently used for, if you look at the top skills that are used in these assistants, they do very basic things.
Mm,
You can set timers, you can check the weather, you can control your home automation, play some music, and these kinds of tasks that are,
yeah,
by the way, all very simple and easy tasks.
yeah,
But the moment you try to do something a bit more complicated with these technologies, that's when they start to fail. And the reason why they start to fail in that one is that because the complexity of the utterance grows, there will be more opportunities for problems to arise. And because of the sequential processing, if there are any problems along the way, those will only surface at the end of the utterance after the processing. And that means that the systems are very poor in recovering for any kind of errors. And while we know that in human face-to-face communication, we make errors, we correct ourselves all the time, we change words, we change the terms we said. And this is something that the kind of the sequential user experience processing is basically unable to fix, because it relies on having to wait. So I would say that this whole user experience thing is still the biggest bottleneck in the wider adoption, and that is holding back. And the moment we're starting to see systems that are using more powerful technologies that are able to do real-time processing of the speech, we will start to see applications where the user can utter very complicated utterances, and then the systems are able to pick up in real time information needed, and the users can change their mind. They can correct something if they said wrong, and they can easily process more complicated things. So I would say that is the most biggest problem at the moment.
I see. So,
And
so what I'm hearing is that, from a technical standpoint, because it's a turn-based dialogue, if you speak as a human being, and human speech is more incoherent, right? It's not very straightforward as commands, in general, right? I mean, of course, when you speak to Alexa, you give a prepared command, but in general, it's much more
mhm.
incoherent. These sequential based models, what I'm gleaning here is that they're not very good at processing incoherent speech and figuring out, okay, what do you want, right?
Yes, and if
From
you consider
if you
human
take the whole sentence.
communication, yes, and if you consider human communication, it is very incoherent, and there's
Yeah,
always corrections and errors, and that's the nature of human communication. And computers are precise, so there is a
yeah.
mismatch there.
Yeah. So when you talk to me like, hey, can you do you have some chocolate? Or actually, you know what? I want some ice cream, but I like chocolate ice cream. By the way, I've met this friend recently who had really good ice
Mhm.
cream at his house. So I'm thinking like you go in this long journey of just talking about 500 different things in the middle, and
Yes.
then if you take that into a turn-based sequential system, you take this whole story about you liking chocolate and you getting fat and you trying to diet, and then your friend is also dieting, and then you still want some chocolate, then the system is going to fail because it's too
Mm,
complex. Even though you're not saying something super complicated, you're not talking about rocket science, is gonna the
mm,
turn-based system fails because of that reason, right? It's trying
mm,
to
mm.
make sense of a very incoherent sentence instead of following it one by one and figuring out, oh, towards the end, and ultimately you want chocolate, let me get you some chocolate, right?
Yes, yes. Hey, there was one more comment I wanted to make to your previous question
Yeah,
that was focusing on the kind of, you were asking about the computational kind of
yeah,
limitations and whether those are limitations. So and these models are absolutely huge. So a couple of points to that. So first of all, when you think of machine learning and training deep neural networks, training is extremely computation heavy, but inference is not that much. So that means that when you've actually made the heavy lifting of training the deep neural networks, the inference part is a bit faster, and that is something that can be more
yeah.
easily done even with kind of like less compute available. And of
Mhm.
course, nowadays in the kind of era of cloud, of course, that can be offloaded the compute into the
Mhm.
cloud, so you don't always need to do it on the edge. But even in the edge, you can do the inference of very complicated neural networks even on device. So that's one part. The second part also, I think that there is a misconception when it comes to natural language understanding, and especially I think that that's where models like GPT-3, they've been amazing for the field, but they've also done some they've also in a way hurt the field a bit, because when people think about natural language understanding, and they have learned about GPT-3s, they are starting to think about generic natural language understanding.
Yeah,
So kind of like artificial general intelligence that is able to understand everything that people are saying with the parity of a human person. And that is, by the way, something where I personally believe that we are still very far. So we are
yeah,
at least 10 years off of being able to do artificial general intelligence level of natural language processing, even with the amazing models of the GPT-3. But
yeah.
that's not even the point, because if we are still at the stage where we really haven't seen a lot of applications that are able to uh, make computers use the sense of speech, in a way equipping computers with sense of speech as part of artificial intelligence, making them understand speech. Most of those applications, or basically all of the applications, are domain specific.
Yeah.
So that means that there is always a limited domain. It's kind of like if you go ask a plumber how to sew something with a needle.
Yeah.
It's a plumber. Plumber knows plumbing. You don't ask a plumber about something else. So even with humans, there is no such things as general human intelligence, but there
Yeah.
are different domains where people are experts, and different people are experts in different domains. And for us to see real valuable applications of speech as part of artificial intelligence systems, it's important for us to understand that the applications are application specific. And when it comes to the application specific task of understanding the language as good as possible in the application's context, that is again something that is in a way a bit more less complex problem than creating the generic understanding of all language that humans may be speaking. And that
Mhm.
again in a way simplifies and I think that there's also this illusion that comes from the marketing of many of these technologies already. When Siri was launched, there were just huge expectations given to this technology, and the field is still in a way struggling a bit because the technology wasn't ready to fulfill all of those expectations, and it still
Mhm.
hasn't fulfilled all of those expectations. And same thing, for example, when Google launched the duplex one, which is this technology that can make human sounding phone calls and
Yep.
can handle different tasks. Like, for example, in their demo, they were booking a barbershop appointment. People think, wow, we're already at the stage where there is this artificial intelligence that can do all of these things. Not that, for example, is also a domain specific agent that basically proactively controls the communication by bringing it forward. So it has
Mhm.
nothing to do with artificial general intelligence or the general ability to understand language or generate language or communicate with people, but it's
Yeah.
basically a very smartly and amazingly well done kind of decision tree to drive people in executing and giving them the information the system is basically looking for.
Mhm. Yeah, absolutely. Absolutely makes sense. Like we said, once you have the intent and the entities from a given speech, and you're able to make sense of all the different entities and intents in that sentence or whatever the person is saying, um, you don't have to you don't have to be omniscient or omni intelligent or whatever to respond. You just need to have a context, and within that context, if something fits, you give them a response with whatever you already know, and you don't have to. And if this go outside of that, you can just say, hey, I don't know, or I have no ability to answer that question, right? Simple as that. It's like
And it's
humans.
yeah, it's not relevant. If you're calling a restaurant to book a restaurant table, they want to know how many you are, what
Yeah.
time are you coming to, do you have any special requests? But then basically they don't interested in what are you wearing today or what is your favorite color or things like that that are kind of like out of domain or out of context from their perspective. And that's
Mhm.
really that's the key in also I would generalize this as a key for artificial intelligence researchers and companies building artificial intelligence powered systems that of course everybody in the field wants to see in a way or some don't want, but this kind of like movement towards these smarter and smarter general intelligence level systems that are able to work really in a robust way to support many use cases. But that's more a kind of science fiction fantasy, whereas the real value of artificial intelligence actually comes from being able to better solve domain specific, well defined use cases. And
Yeah.
that's where the real power and the value of artificial intelligence goes. So this is sci-fi fantasy is trying to create these artificial intelligence robots that look like humans. That's a very
Mhm.
different field where the
Yeah.
really practical applications of AI are something very more simple, focused on the task that needs to be solved and leveraging all the possible modalities and technologies and inputs basically available
Mhm.
to the system to solve the task as efficiently as possible.
Yeah, yeah, I totally agree, Otto. In fact, one thing that I teach is that if you have a business, your business is essentially a list of several hundred or thousand of things that need to be done, right? And what the best way to find use cases for AI is which of these things they have to be done somehow, whether they get done by software or a human being in Indonesia or whatever, and each of those tasks can be picked off by a machine learning model or an automated system. That's literally AI. Like, you don't need to have an AI CEO who can run your entire business and make the decision for you. Not yet. I mean, maybe in the future. But yeah, I totally agree. So that's a good segue into your company, right? Let's finally talk about you. And, and to keep it flowing, let's start with before. Let's treat your system as a black box and see, given the context of, we talked about how the traditional voice assistant technologies fail at certain things and excel at others, which gap in those applications do you fill? And we'll just take an
Hmm.
example of some applications about to see the magic, and we will have a video of a demo of your product right afterwards. But before we insert that, maybe you can give me a more big picture perspective.
Absolutely, absolutely. So, Speechly is basically the fast, accurate, and simple voice interface API. And what our technology allows you to do is to build these kinds of real-time voice-powered applications, whether it's on the web, whether it's in the mobile applications, whether it's in domains like e-com or professional work. So it's really about powering developers and product teams in building better voice user experiences. And the secret or the core functionality or benefit of our technology is that we basically recreated and redeveloped the whole voice technology stack from scratch to
Oh.
avoid the sequential processing. So while basically all of the traditional systems do the sequential processing that I was explaining, our system actually does all of that in real time, or actually the spoken language understanding part of that in real time. So that means that our core technology is able to process in real time when the users are speaking what the user is actually saying, not having to wait until the end, but they be able to do that in real time and then passing that information back to the application so that the application can respond. And Speechly is a developer tool, so that means that we power teams that are building applications that could benefit from voice into creating more efficient, faster, and accurate applications.
I see.
And
So, I see. So to summarize, from the perspective of what we were discussing earlier, when they were going from speech to text to entity and intent, and then you send that to the application, and the application has that business specific domain knowledge. In your case, it's speech to entity and intent, or is it speech to what? Like, what is the output?
it Excellent question. So it is from speech to intent and entity in real time in a streaming manner. So that
I
means
see.
that while people are speaking in real time, extracting the intents and entities. And why this is meaningful is that this allows the developers who are building these user experiences and user interfaces to actually make the user interface react in real time. And
I see.
the value of this really comes when you are building multimodal interfaces, which basically use voice and graphical elements to create very efficient user interfaces. And the ability for the graphical user interface to react in real time to the user's speech is something that actually makes solving quite many, a bit more complex tasks at least 5 to 10 times faster. And that's something that the productivity increase of that one is quite huge.
I see, I see, I see. So, and we're going to insert a demo here if you're watching on video. But if not, let's take an audio example, right? Let's say streaming is the key word here, where instead of having the turn
Mm.
by turn dialogue, as soon as you start speaking, the machine is already outputting entities and intents that the
Yes,
application can start reacting to. And by the time you're
yes,
finished, you already have the reaction of the
exactly,
machine
exactly.
instead of waiting for them to
Yeah,
process the whole incoherent speech. So you can see the
yeah.
machine reacting and changing its reactions as you give it new information.
So here goes. Yes. Book a general practitioner's time for tomorrow afternoon. My symptoms include dry cough, high fever, and feeling like shit. I could also do today morning. So this is an example of a search type of a use case where the user is trying to find something. And this example comes from the e-commerce domain. So this is an example e-com store. It's got departments, product categories, brands, colors, sizes, and so on. But you can actually speak to the store. Now, when I'm speaking to the store, please notice how the store reacts. It is not providing a response with a synthetic voice and waiting for me to finish, but it actually starts to react the moment I start to speak to the store. So, check it out. Show me men's sneakers from Nike. In white. Actually in black. And show me in size 10, please. And could you show me the cheapest ones first? Actually show me the white ones. And here's an example from another type of user behavior. Book a one-way flight from New York to Boston, departing next Sunday for 2 people in business class. And can you show me the direct flights only? So you could see there that while I was speaking, I got the real-time feedback visually from the system, that I got the confidence to actually continue, and I was able to execute a fairly complex task very, very fast.
and if it's not, and like I said, people make mistakes, systems make mistakes, there will always be mistakes. If
Yeah.
there are mistakes, you can immediately fix them. Oh, actually the
Mm.
address is this one. Oh, it was this number, or the telephone number or something. So it makes you very fast and intuitive way for you to provide the information. And that again is another task that can be done at least 5 to 10 times faster than if you would try to do that, for example, with the graphical user interface only. So there's a couple of example use cases where this kind of real-time spoken language understanding technology really can make a difference in making it easier and faster for the user to execute the task.
Yeah, makes sense because as you're speaking, you say, "Oh, I want milk, I want 6 eggs, I want bananas and whatnot," and you say, "Oh, I don't need eggs," because it's streaming instead of collecting it in one sentence before it processing. It's streaming, so don't want eggs. Okay, that's a new intent and entity information that's
Mm.
added to the stack
Mm.
in a way, and then you can immediately
Exactly.
process that. Okay, just remove the eggs because it seems like they don't want
Yes,
eggs, right? Instead
exactly.
of saying
And that
I
happens
want eggs and then I
instantly.
don't want eggs, and then having those conflicting information in a typical system, it wouldn't work out, right? Or it would confuse the
Mm.
system depending on how well they've designed their software to work. But here, you can quickly have a much more reactive interface. Okay, that makes sense, and we'll have.
Yes,
I'll figure out how to fit in the demo somewhere in between. Okay.
sounds
So
good.
the next thing. So now let's open up the black box, right? So now we see that this is really cool and it works, and we can see the user experience improvements that could really be the deciding factor in driving this technology's adoption, at least in certain applications where it is much more valuable to have real-time conversation than a walkie-talkie conversation.
Hmm.
And I know you've patented this technology, and so it's not a trade secret, right? Let's start
No.
with how does it work at the high level, right? And then we will get into what was the reasoning or decision, process for patenting it versus keeping it a secret.
Yes, sure. So the technology is based on a deep neural network, and it's a very specific type of deep neural network that is able to handle streaming audio, and that's kind of like that's the really the secret sauce of our technology. And
Mm.
how that network is built, we have released white papers where we reveal some of the kind of like design choices we've made.
Mhm.
But of course, our probably biggest trade secret is really on how that works and how to train the model and how to do the inference on that model. And that is something, that part is something that you cannot patent. You cannot patent a deep neural network.
Yeah,
So that means that our IPR strategy relies on a combination of trade secrets and patents to really protect our IP. And we have patented quite many different parts of the stack that are able to be patented. We have patented how the user interface works. We have patented how we do the adaptation, how we train the models in the machine learning context. We've patented how we do some of the real-time aspects of the deep neural network processing. But of course, the deep neural network as such is something that cannot be patented. It's a bit
I
like
see.
software.
Yeah, I see. So if I understand correctly, the actual architecture of the deep neural network is a trade secret.
Mm,
I see.
yes.
And what you've patented is the way you is the training process, or like, can you explain to me what are the different blocks of this, or what are the different moving parts at a high level, so I can make sense of why like certain
So
things were more likely to be better to be patented.
yes. So of course, to get the final details, you will need to talk to an IPR lawyer.
Yeah.
So we have talked to our IPR lawyers lawyers on this, but to protect our IP, because you cannot patent software or deep neural networks, but you
Mm-hmm.
can patent different methodologies and other things. So we have
Yeah,
patented the methodologies we use to train our models, which are quite unique.
I see.
And we have also patented some of the end user mechanisms of the user interface that our technology allows. And that's again something, it's not the software itself, it's the methodology, it's the functionality, which is something that you can patent. And we've also patented some of the methodologies we use to actually be able to boost the accuracy of our technology by adapting it to the domain. So that means that if you're figuring out a IPR protection strategy for your artificial intelligence system, I think it's important for you to understand that because you cannot patent the software part of your artificial intelligence system, you need to then protect the interfaces where that software interfaces with the applications, and that's where you
Mm-hmm.
can actually do the patent. So it's very important for you to be very smart and strategic and figuring out what part of your IPR is unique, and what is something that you can actually patent to protect your core.
Mm-hmm. Yeah, love that. Love that. I think that's going to be really helpful to a lot of the people who are listening who might be working on similarly interesting AI products, because we have an audience of CEOs of AI companies and whatnot. So this is going to be helpful for them. So to wrap this up, what people get from you is an API. And how do they use the API? What do they like? How does it work?
So the API works so that the developer or the product team using it first needs to configure it to support the language of their domain. So let's say that if
Okay.
they're making a restaurant booking application, they need to just explain to the system, configure it to support the restaurant booking domain. When they've done that, they integrate that into their application, and we have ready-made SDKs. So if you're building web applications, you can use our JavaScript or React SDKs. If you're building in mobile, you can use our iOS and Android SDKs. And it basically works so that you copy paste a snippet of code, and that adds the voice functionalities, and you link that back to the application ID that you've configured to support your domain, and then you're done. So it's very easy for anybody building anything on the web or on mobile devices or even any other system that has a microphone to access the speech technology and add voice as part of their product.
I see. So when you say they configure the API for the specific domain, and let's say I'm building a platform for restaurant bookings or restaurant food recommendations or something like that, you're saying that your system already has some domain, specific configurations, or what does that mean, domain specific configurations, or how does that differ from the domain knowledge that I have to build into my system or into my
Mhm.
application?
Yeah, very good question. So I think that one problem of the existing natural language understanding technologies out there is that they try to provide a general industry level natural language understanding solution and fit that to many use cases. And that's great. It brings you to maybe 80% of the greatness of the use case. But the moment if you're a company implementing them, you want the system to understand your specific product names, your competitor names, your process names. You have a lot of very specific knowledge in the domain that you want to get implemented, and that's the problem of these off-the-shelf natural language understanding models that you get. They are okay
Yeah.
for bootstrapping, getting you to some level pretty fast, but if you want to create a truly magical experience that people are actually willing to use again and again and again, then you really need to tune it to be very well tailored to your specific domain. And this is something that we've learned building some of the current generation of these technologies. So our founding team has members who have been building Siri at Apple and Alexa at Amazon, and we have consolidated those learnings into better solving these problems that the current generation are still doing. And like I said, for you to be able to create a really magical user experience, you need to be able to configure it to your specific domain. And that's why our approach is that instead of trying to create something that is okay for many people but not perfect for anybody, we've actually created very easy to use configuration tools so developers can really nail it for their specific use case. So their brand names, their usernames, their whatever there is. And of course, we have a library of standard entities. Our system can understand numbers, addresses, email addresses, alphanumeric sequences, and there's a lot of ready-made components that you can use, but nobody can know how your specific users and your business works. But we can give you the
I see.
tools to make it super easy for you to make it perfect for you.
So they have to. So in summary, they have to train or fine tune the model on new data based on their domain expertise. Is that what you're saying?
Yes, and they can do that. They can bootstrap it by imagining how the users might interact, and
I
then
see.
when they put the system in live, whether it's a pilot or the production mode, they can all the time monitor how the users are interacting with the system, and then labeling that data, using that to retrain the models, so the system actually adapts into different ways how people are interfacing and behave, like using the system, because developers are super great in kind of imagining great ways how people might use the product. But then
Yeah.
there's the real world where the people
Yeah.
actually might find very weird ways of how they would want to interface with the system. And the only way for somebody to get into that one, it's impossible to know that a priori. It only can be done a posteriori when you have
Yeah.
offered the system to the users. They will try to break it down, and they will break it down.
Yeah.
But if
Yeah.
you're able to have a fast feedback loop in actually feeding that back to train the system, you're able to create systems that work magically.
I see. So the API and the system has an aspect of continuous learning. However, it sounds like there is a gray spot here in the middle where there's some manual labeling involved and some manual oversight involved to get the data prepared to be fed back into the model to keep fine tuning the thing.
Well, first of all, there is the machine learning bootstrapping problem. So how do you
Yeah.
bootstrap the system to work initially when you start collecting data? So for
Yeah.
that one, we've created a very easy to use scripting language that allows you to easily generate hundreds of thousands of training examples with a
I
couple
see.
of scripts of code. So that
I see.
problem we've solved. And then when it comes to the kind of ongoing feedback, so you are absolutely correct that there is a kind of manual data annotation step involved there, because you need to be able to tell the system what's the ground truth, and that's something that only the ones who understand the domain know how to do it. So that's something, and that of course is something that many of our clients feel that they might not have the resources to do that kind of task. So of course, we as a company, we do offer that as a service. So many of our
Yeah.
clients use our service where we actually all the time monitor and improve the model, so they don't need to worry about that. We handle that for them. And the same thing comes for the cold start bootstrapping problem. So we always,
I
or
see.
not always, we often help our clients to get up to speed by creating the initial configurations for them. So it's easy for them to get up to speed.
I see. In the sense, so in a sense, to fine tune the model, since they have a little bit of domain knowledge that they can pre-program, the you use the system of to create synthetic training data, which is and since the synthetic data is so scalable, you can really
Mhm.
fine tune the model to an impressive
Mhm.
bootstrapped start
Exactly.
point, and then you have a little bit more manual input to keep making the last mile improvements. But
Exactly.
but the overall system, if you look at it holistically, is already so much better than using Alexa for your restaurant booking system, right?
Yes, absolutely. And because it's a fully machine learning based system that uses huge amounts of the synthetic data to train the models, it means that it's very robust and it's very well able to generalize. So that means that you can use it. It can understand entities that it has not been taught with. It can understand a lot of information that hasn't explicitly been programmed into it, because it's basically a machine learning based system.
Well, that's really amazing to hear, Otto, and appreciate you sharing your wisdom and your knowledge and being so open and transparent with us. And I'm sure that the community is really going to appreciate that you're willing to educate us about how your stuff works. So thank you so much,
Absolutely.
Otto. It was a great experience, and let's stay in touch.
Thank you, Aman. It was a pleasure. Thank you. And all the best for all the listeners. If you're interested in speech technologies, don't hesitate to visit speechly.com and try our technology, see our demos. There's lots of really interesting things to see there. Happy hacking.
Happy hacking.